current slide and share screen. Okay, so just to remind you, we spent some time last time talking about Newton's 3 laws over here. Newton's first law says something that's a little bit strange. It says, depending on how I'm moving when I watch something, I might see the motion of any object that even you might see just sitting there having some crazy motion because I'm watching it from a point of view that's moving. And Newton is reassuring us in the first law that it's always possible to observe an event where if there are no forces that are acting on it, I look around, there's no electrical forces, there's no gravitational object, big masses nearby that would be pulling on it. There's nothing touching it in any direction. It looks like there's no forces on it. Therefore, if I'm observing from an inertial reference frame, it should be moving with constant velocity. So it's a way of reassuring yourself that you're observing things from an inertial reference frame. The importance of that is that we're going to use that for calculating in Newton's second law. Newton's second law says, hey, if I know the sum of the forces acting on an object, I can figure out what the acceleration is as long as I am observing from an inertial reference frame. F net equals ma. Add up all the forces as vectors using a free body diagram to organize your work, and that will tell you what the acceleration is. And maybe if the forces are constant, that might mean we can use constant acceleration kinematics. We'll do that often in the examples we do today. And Newton's third law just says anytime two objects interact, the force that one exerts on the other is exactly equal and opposite to the force the other exerts on the one, no matter what they're doing, even if they're accelerating or bouncing off of each other, even for that short period of time when they connect. There's a small force against each other, equal and opposite, big force equal and opposite, and small force, and then they bounce off. So it doesn't matter what's happening. That's true at all times. Okay. And the other, so we said we're going to investigate a lot of forces. The only one we got to was the weight force. And we said, if you're near the surface of Earth, you can calculate the magnitude of the weight force. So the Earth is pulling on you in the downward direction. It's pulling you toward the center of Earth. And if you know your mass, you just multiply by little g, and that tells you how big that weight force is. Little g is 9.80 here in Danville. I was telling some people in office hours that little g varies depending on where you go around the Earth, a tiny amount. In some parts of the Earth, it's closer to 9.81. Here it's 9.80, and that's why in the homework you always see they tell you what the acceleration due to gravity or little g is. Most of the time it's 9.8, but you will find a really rare problem where it's 9.81, and you want to use the value they give because they're using that in computing the correct answer, right? And maybe they're from Paris, where it's 9.81. Okay, so let's go forward. We're going to do lots of problem solving today, and meanwhile describe different forces besides weight. So to solve F net equals ma, it's a little bit strange as an equation because it's a vector equation. It says a vector equals a vector, but the only way a vector equals a vector is if you have x, y, z axes, the components equal the components. So that means the net force, or sum up all the x components of forces, that's equal to m times ax, and same thing for y and z. So you can just separately write down x, y, and z versions of F equals ma. But of course, you need to know what the axes mean. And so usually the way we incorporate it into a problem is we draw a free body diagram. Remember, you draw a blob that's the object you want to concentrate on. Hopefully you know the mass of it because we're going to be concerned with its acceleration. And you draw as little arrows what all the forces are. And then you can draw next to it a set of axes that define what the x direction, y, and z direction is. And we'll see this used in examples. So let's start with an example that's sort of a very straightforward one, but just shows the idea of how to create these free body diagrams. Here's a crane lifting a 185 kilogram steel beam upward from rest. So we're imagining the cable had the beam just hanging from it, and then they start accelerating it upward or lifting it upward. And we'll see if it accelerates. The cable applies a 1,960 Newton force upward on the beam via the cable. And so we want to find the net force on the beam and the beam's acceleration. And then once we find the acceleration, we'll find out the acceleration's constant because all the forces are constant. And then we can do a little kinematics problem. How far upward has the beam moved after 3 seconds, right? We're given a delta t, and we want to know maybe a delta y. As long as acceleration is constant, we can do that with kinematics. Okay, so our rules for these using Newton's law is always going to be first draw a free body diagram. That's a very crude drawing of the thing. You don't want to be artistic. I'm just going to draw my beam as a blob, and I'm going to label its mass in the middle if I know it. And then choose axes. So next to that beam, or next to the blob, I'm going to draw some x and y axes. So I know if x is this way and y is this way, or maybe they're tilted or something crazy like that. We'll see it's useful to use tilted axes, as you've also seen in the reading. Once I know the axes, I can use f net x equals max and f net y equals may individually and hope for the best. So this is a very simple case. Here's my beam. I just drew it as a blob. It was supposed to be a rectangle, but it doesn't quite look like it. Since I knew its mass, I put the mass in the middle of the blob just so I know what the blob refers to. Since I'm not being very artistic, then I can say, oh, 185. Oh yeah, that's the beam because it's labeled as 185 kilograms. Okay, and we're told that there's a force. I'm imagining the Earth is down below in the way I'm holding the page. So there's an upward force from a cable pulling on it with a 1,960 Newton force. And so I'm drawing that in as an arrow. And conventionally, when we draw free body diagrams, we always attach the tail of the vector to the object so that even if I had an object that I were pushing in this direction, so imagine I'm pushing this object in this direction, and I want to draw my force that I'm pushing with. You might be tempted to do this, but we never do that. We always attach, we say, I'm pushing to your right, and therefore I'm going to attach the tail and have the head going to the right, even though I'm pushing from this side. It looks like we're pulling from the other end, but it's not going to make a difference. Okay, there's a force. Are there any other forces acting on this object? Because when we apply F net equals ma, we've got to have all the forces that are acting on it. Anybody see any other forces that are acting on this beam? Yeah. Gravity's acting on it. So the gravitational force on an object is otherwise known as the weight force. We know how to calculate that. It's just m times little g, m times 9.8. So here I'm labeling, this poor thing always sort of gets out of whack. I'm labeling the length of these force vectors. This one I didn't compute, but there's how to compute it. 185 times 9.8. That's how big this downward gravitational force vector is. And assuming there's no great air resistance, that seems like all there would be. Yeah. Well, because these numbers that I'm drawing on the diagram just represent how long the vector is, and the direction is given by the direction of the vector. We are going to turn those into components, which may have plus or minus signs associated with them. So notice that was the first thing. Draw a free body diagram. Then I've got to choose axes. Now, nothing's really happening in the horizontal direction. I could choose plus x going to the right or something, but I don't really need to here because nothing's happening in the x direction. But it's important that I choose plus y, or I could call this plus x, it doesn't matter, plus y either up or down and be definite about it. So I usually draw that next to the free body diagram. And that's going to allow me to know what f net y equals may means. I've been definite about it. Yeah. No, because we're working in SI units, and it's tempting to think that the SI unit should be grams, but the SI unit is actually kilograms. So as long as I have everything in SI units, I tend to suppress the units. I haven't done that yet, but you'll see in the work that follows, I probably start dropping the units. If everything's in SI units, then I know if I calculate something, I can just slap the SI units on it, and I don't have to carry all that stuff along. Okay. So I've defined the y direction. Now it makes sense to say f net y, or as Giancoli, I believe, writes it this way. This means the same thing. The sum of the force y components. That means that's, the net force means add them all up, the y components. So he writes it that way. Okay, so, and I'm gonna set it equal to m times ay in a second, but let's put them all in. So the 1960 comes in with a plus sign because look, this vector going from tail to tip is moving in the plus y direction, so its y component is positive. That's not true of the weight vector. Net means add them all together, so I've got to add together the y components. Here's another y component, and that's a negative y component. So whatever that product is, I've got to put a minus sign in front of it, because in going from tail to tip, it's going in the negative y direction. Okay, so that's an expression that represents the net force y component. And when I plug that in my calculator, I get 147 newtons. And then I'm going to set that equal to m times ay. That's Newton's second law, y components, right? M is 185 in SI units times ay. And then I can just simply solve for ay by dividing out the 185. Oh, I guess I'm boxing that because I also asked to find the net force. So the net force is 147 newtons. It's going upward because its y component is positive and not negative. And find its acceleration. So then I divide that number by 185 and I get 0.795 with a plus sign in front of it. The plus sign means its acceleration is positive y. It's in the positive y direction. So if it's starting from rest, it's accelerating up faster and faster and faster in the upward direction. All right, so that's great, not too hard, but that's the basic idea of how we use it. And now I can use that acceleration the whole time, starting from rest until it goes faster and faster and faster. That acceleration is constant. And therefore, I can use that to help me solve a constant acceleration kinematics problem. And sorry about that. I guess I also put on here just for, if I had put an x-axis, say, going to the right, there weren't any forces with non-zero x components. So the net force x component would be 0. And therefore, when I divided out that mass, I'd get that ax is 0. We probably knew that already, that it's not going to start accelerating in the x direction if all the forces are aligned in the y. Okay, so we're told in B, the beam begins at rest at t equals 0. How far upward is the beam moved after 3 seconds? That sounds like a kinematics, right? T equals 0 is when it starts from rest. The final is when it reached 3 seconds, right? It's still accelerating upward there, so the acceleration is constant. And here's a relevant equation that I could use, right? I know t, and I want to know y. So I use the y versus t kinematics equation. And let's plug into that. What's y initial? Well, I didn't do a careful job of drawing my axes on here, but I might say whenever it starts at rest, I'm going to say the middle of it is at y equals 0. So I'm going to take y initial to be 0. It starts at rest, so vy initial is also 0. Those first two terms go to 0. We know the acceleration y component that goes in there is positive, so I put plus 0.795. Don't be fooled and put 9.8. It's not in free fall, right? There's the crane pulling it up. And then the time since initial is 3 seconds. And you calculate that, you get 3.58 meters. Okay, that's the most basic kind of bare bones application of this. It's really a one-dimensional problem. But we'll see, we'll very quickly apply this in 2 dimensions. Any questions on that before we move on to slightly more difficult problems? Still one-dimensional problem, but it's going to be a little bit trickier. Okay, so here, and I should say this is the worksheet I passed out in class, but I should say for the Zoom folks, this was posted as the worksheet, first worksheet for today in class. We'll be using the second worksheet too. So we're now on the backside, problem 2. An 80-kilogram man in an elevator stands on a scale that reads in newtons. And we're asked various things. If the elevator is stopped, just sitting there, what does the scale read? If the elevator is moving steadily upward at 6 meters per second, what does the scale read? If the elevator is accelerating upward at 3 meters per second, what does the scale read? Okay, we got to think about this. But let's do, I think I have the first one to do together here. So again, we're concerned, at least it seems like we're sort of concerned about the person, right? The person is pushing down on the scale, but the scale is also pushing up on the person. And if we want to know what the scale reads, you might think, well, I want to know the force on the scale, right? Scales are calibrated, so whatever the force is that's being pushed down on them is what they're supposed to read, right? However hard you push down on them is what you're supposed to read. But however hard the man is pushing down on the scale, we know from Newton's third law that the scale is pushing just as hard up on the man's feet. So if I can find the magnitude of that scale force, which is pushing upward on the man's feet, I know that's what the scale reads. The virtue of using the man and not the scale, so you see I've labeled this as 80 kilograms, that means that's the man as the subject of my free body diagram, is I don't know the mass of the scale. And there's going to be another force on the scale from the floor of the elevator, and that's kind of hard to get at too. So I don't really know enough to work with the scale, but I know the man's mass, and I think I know all the forces on the man, and one of them is going to be related to what the scale reads. It's how hard the scale is pushing up on the man. It's the same as how hard the man is pushing down on the scale. Okay, so the elevator is just sitting at rest. We might draw a little cartoon. I'm hoping I'm drawing this big enough that I don't have to change. That's not what I want to draw. Let's draw an elevator just as a box. So here's the person sitting in the elevator. Here's the guy. Well, he's got his legs flying up in the air. There we go. Here's the scale down here. Maybe a digital scale or something like that. And it happens to read in newtons, right? And there's a cable that can pull it up or lower it down by accelerating it or pulling it at constant speed or something like that. Okay, this is the very simplified bare bones version. Now I want to apply Newton's law. So what else do I need besides those forces? And I guess I should ask, are there any other forces besides the ones I've labeled? The scale is pushing up on the man's feet. We're concerned with forces on the man. Just like I can feel the floor pushing up on my feet. I feel that pressure from underneath. If it weren't, I'd be in free fall going down towards the center of the earth. So there's a force up from the scale, but of course, anytime you're near the surface of the earth, earth is pulling down on you with a gravitational force. So there's mg down there going down, just like it was for the beam. And the scale, in this case, there's not a cable pulling up, but there is a scale pushing up. And we're imagining the person's just sitting there, not accelerating at all. What else do I need in order to apply Newton's second law? I'm not ready to say F net x equals max or F net y equals may. Why not?
Is it because there isn't, oh, I'm sorry.
Go ahead.
Is it because there's not an IRF that's defined yet?
Well, yeah, I mean, I'm not sure if you're getting at the same thing I was thinking of, but maybe you are. It's that I haven't defined what the x and y directions are yet. Okay, and you may be thinking in your head, oh, y is always up, but that's not true, and it doesn't have to be. In fact, we'll see problems in the next worksheet problem where we're not going to want to choose y as up. We're going to want to tilt the axes. But in this particular problem, we want to choose plus y either up or down. And again, there's no forces acting in the x direction, so x is not going to be very interesting. But we could put the x-axis perpendicular to it, going horizontally. But now when I write F net y equals may, I know which component should be positive or negative because I've drawn plus y going in the up direction. Okay, so let's write down F net y equals may. I wrote it here, and the first thing I'm going to do is simplify the right-hand side, the may. Why did I put a 0 over there? They're not moving, right? One way to not accelerate is just to sit there, right? Also moving at constant velocity is not accelerating, but this is another way to not accelerate. It's the most common way that we don't accelerate. We just sit there. So the right-hand side simplifies to 0 if you're not accelerating. The left-hand side, of course, I've got two forces going in there, and one of them, in this case, I don't know, but it's what I want to know. So I'm going to use this equation to solve for it. So let's plug into F net y. Two y components. One of them is a positive y component. That's the scale, comes in with a plus sign. So the F scale, which I don't know, I'm just going to put a plus sign in front of it because in going from tail to tip, I'm going up in plus y. And the 80 times 9.8, I'm going to put in with a minus sign. Okay, so here's F net. The weight comes in with a minus sign. It's a negative y component. Scale comes in with a plus sign, and I want to solve for that. and they add to 0 because we're not accelerating in this case. And so the scale should read 784 newtons. You know, in the US, we don't have much intuition about newtons, but sure, that's fine as a weight force in newtons. Okay, what I want you to do is finish up this worksheet, especially try to work on B and C here. So now we're going to change the situation. We're not just sitting there. In B, you're cruising upward at 6 meters per second. In C, you are accelerating upward at 3 meters per second squared. And in D, I believe the cable breaks and you go into free fall downward. And we want to know what the scale reads in each of those situations. So try that. Feel free to talk to whoever's near you. I know you're not right next to someone, so it's hard to look at their paper, but if you get a chance, or if you're not sure, or if you just want to check your number with your neighbor. And while I'm taking this break, I'm going to pass out the next worksheet, which we'll start on shortly. So if you can pass these back. This one we'll be working on today and Friday. It's a bunch of pages stapled together, but we're just going to practice lots of problem solving. Wait till most people, it looks like, are at least working on C before we come together. We can discuss D together. Some of you are almost done with C and some of you haven't started quite yet. Someone on the reading responses said they had never seen a spring scale before. Is anybody willing to admit that? All right. The kind of thing you see in the old days, people would hang a fish on, and it compresses a spring, and it just, you hang a 2-pound weight on it, and you put a 2 there, right? And if you hang a 4-pound weight on it, it goes farther down, and so on. So there's a little spring inside there, and you're compressing the spring, and that causes this thing to twist, and you can just mark it. You hang different weights on it, and so if you don't fish, it's probably not something you see too often. And nowadays, I'm sure they're all digital. Okay, let's come back together and look at the rest of this problem. So we want to compare. Does the scale read more or less in these cases? So in B, the whole elevator is moving up at a constant speed of 6 meters per second. Let me just look, starting with the same free body diagram. Is the weight the same? Yeah, I mean, maybe we need to say that explicitly, but your weight depends on where you are relative to Earth, right? Your weight gets smaller as you go far away from Earth. But it doesn't matter on how you're moving, right? Whether I'm moving this way, that way, up or down, accelerating or anything like that, going around in a circle, my weight force is the same. It always points toward the center of Earth. And if I'm near the surface of Earth, then the appropriate value of G is 9.8. The scale force, well, is it still up? Yeah, it's still up, and it's still unknown. We want to still solve for it. I can still choose plus y up. That's my choice there, right? So when I do F net equals ma, I'll write it the Giancoli way. The sum of the force y components equals may. Nothing's going on in the x direction, so that's not very tempting. What changes on the left-hand side? Nothing, because the F scale is still my unknown. So I'm still going to get F scale comes in with a plus sign because it's pointing in the plus y direction. And the mg comes in with a minus sign because it's pointing in the minus direction. How about on the right-hand side of F net equals ma? That was 0 before because I was just sitting here. Now, how about this case? Yes. It's still 0 because another way to have 0 acceleration is to move with constant velocity. Seems like you might get something out of it, but Newton's second law is telling us what matters is the acceleration, not your velocity. So even if you're moving up at 100 meters per second, scale's going to read the same thing. And that means that physically you will feel the same. You're not feeling like you're crushed into the scale or lightweight or something like that. So in this case, the solution's the same. I mean, this is the same exact equation we got before. 784 newtons, no difference. What matters is the acceleration. In both those cases were 0 acceleration. So the point of C is it really is a different acceleration. Here you're accelerating up at 3 meters per second. Hey, I like to reuse stuff because I'm lazy. How does the free body diagram change when I'm accelerating? Does the weight force change? Is the scale force going to change? Well, it might change, but it's still my unknown. I still want to solve for it. In fact, we'll see that it does change, but it's still going to be pointing upward in this case, pushing on the bottoms of my feet. So the left-hand side of the sum of the force y components equals may is exactly the same. I'm going to choose my same y-axis direction. F scale minus 80 times 9.8. But it's the right-hand side that's different, right? M is 80. And AY is what in this problem? Plus 3, minus 3, plus 3, because it's accelerating upward, right? And that means the acceleration vector points in that direction. That's a positive y component. See, I'm dropping the units because everything's in SI units. And that means if I solve for F scale here, I'm going to get something different. F scale then is going to be 80 times 9.8 plus a little bit more, right? If I put them together like that. So I'm going to get a number that's bigger than the weight before. When you work it out, this is 1024 newtons, 1024 newtons. So that means when you're accelerating upward in an elevator, and you've had this experience before if you've paid attention in the elevator, you get in an elevator, it's at rest, you press a higher floor, and you start accelerating upward. It only happens for like 3/4 of a second until the elevator gets up to speed for most elevators. But during that time when you're accelerating, you feel kind of heavy while you're accelerating up. So it's not just that the scale reads more, like I feel in all respects as if I'm heavier. Now, I wouldn't actually say I'm heavier. When I say I'm heavier, that would mean my weight is bigger. My weight's the same. This is my weight. I haven't gained any weight, but I feel as if I'm heavier because I'm accelerating upward in this case, and that's registered on the scale. Okay, and similarly, if you accelerate downward at 3 meters per second squared, what would have changed in this? This would have changed to a -3, and then I would have had a minus sign there, and the number would have been less. So if you're going upwards, but you're slowing as you go to the top floor, you kind of feel like, oh, I'm a little bit lighter than usual, and the scale will actually read less on the floor. Okay. Any questions on these? Let's just, before we talk about D. Just to put it in the same context, now, the poor person's in this elevator and the cable that's pulling it up breaks, and all of a sudden they're in free fall. Okay, we don't know what the scale force is, but let's put one in there. We'll solve for it the same way. Like it's just a placeholder, and we're going to solve for it later on. Doesn't matter if I'm in free fall. The Earth is still pulling on me downward. However you're moving, the Earth pulls on you with your weight. And so this free body diagram is exactly the same even in D. And the plus y direction is still a perfectly fine choice. So the left-hand side of the sum of the force y components equals MAY is exactly, this is getting kind of boring, right? F scale minus 80 times 9.8. What's different about the right-hand side? What's my acceleration y component if I, along with the elevator, am in free fall? It's negative 9.8, right? I already chose plus y is up. So that means if I'm in free fall, my AY is minus 9.8. I'm accelerating towards Earth. So if I'm in free fall, that's the one case we already know the acceleration. It's toward Earth, 9.8 meters per second squared. That's a negative y component. And what happens here? Well, I've got the same negative factor on the left-hand side and the right-hand side, and that means F scale is 0 in D. Everything's in free fall. So it's like the scale's in free fall below me, and it may be just hovering a millimeter below my feet, but we're both accelerating at the same rate towards Earth, towards our impending doom at the bottom. Any questions on those?
I have a question, Dr. Kelly.
Yes.
What is the right-hand side of like the equations that we've been solving? What does that represent on our illustration?
It's not represented on the illustration. This is just telling us about the left-hand side. And then we use F net equals MA to conclude what the acceleration component is going to be. And then we might use kinematics to figure out how far something's moved if the acceleration is constant. So it has nothing to do with the right-hand side. It only tells us how to compute the left-hand side with the correct signs and all that.
Okay, thank you.
Mm-hmm. All right, let's go back. I'm not sure if there's any more before the next. So you guys have done those. I think I want to start by just discussing this next problem. Here's where we're slowly stepping up and ratcheting up the difficulty of these problems so that different complications come in. And now we're going to consider something going on a frictionless plane. So this is like a plane that's inclined to the horizontal, but it's got like wet ice on it. So when you put something on it, there's really no friction holding it back. It just accelerates down really quickly. And we are told it's an 8-kilogram box. We release it from rest. So we place this box on the incline and let it go, and it starts accelerating down the ramp, right? It's a straight ramp. And the ramp is inclined at 25 degrees to the horizontal. Maybe I should draw a picture of it. And I bet I have a picture once I start clicking ahead. Find the magnitude of the box's acceleration. It's going to accelerate down the frictionless ramp. And how far it moves in the next 2 seconds. Hey, that sounds like a kinematics problem. If the acceleration is constant and you give me a time, I can figure out the displacement in those 2 seconds, right? So we're going to keep adding those on to the end of problems now. That's why we emphasize those at the beginning. So here I'm drawing a cartoon that sort of describes what's on there. 8-kilogram box, 25 degrees to the horizontal. It doesn't look very horizontal, but that's supposed to be. And what I'm going to do is draw some X and Y axes, and I'm going to try to explain to you why this is a bad choice. It's very tempting to do what we've always been doing and take X horizontal and Y vertical. If I do that, here's the problem with that. I know which way this thing is going to be accelerating when I let it go. Which way is it going to be accelerating? Straight down toward Earth? To your right? No, it's going to go down the ramp, right? The direction, it's going to be doing one-dimensional motion. Its acceleration is going to be along the direction it's speeding up, right? So its acceleration is going to be down the ramp. I think I've got that in here drawn. Of course, this isn't working. Okay, so here's my acceleration vector. It's a little hard to see. It's in green there, but choosing this is a poor choice because A, I know points down when I let it go, it's going to start accelerating in that direction. And that means I'm going to have, if I want to know the acceleration, I'm going to need to figure out what AX is, and then figure out what AY is, and then take the square root of the sum of the squares to get the magnitude of the acceleration, which was what was asked about in this problem. I'm just making more work for myself. I've got 2 unknowns. Compare that to the other choice, which we're always going to choose, at least for these kinds of problems. Anytime you know which way something is accelerating, you should take one of your axes aligned along that direction. So in this case, I've aligned plus X. I've tilted my axes, and we're going to see that makes our algebra much simpler, so that X plus X aligns along the direction of the acceleration, and plus Y is perpendicular to the tilted plane, perpendicular to the acceleration. And that saves me work. I mean, if for no other reason, you can see, look, automatically I know that AY is 0. To go from tail to tip of the acceleration vector, I don't have to move along Y at all. So AY is 0. It's all AX. So if I find AX, I'm done. I just need to solve for one variable. That's a lot of savings and work. You could do it the other way. It's just more work. So we're never going to do it that way. We don't want to make more algebra for ourselves. So there's my axes. Okay. That's a cartoon drawing. It's helpful to draw that, but now I'm just going to really pare it down and just draw that box, 8 kilograms. I've labeled, I know it's a little bit small and messy here, but it says 8 kilograms. I drew my box a little bit tilted so that it looked like it was going on the plane, just to help me get the feel of it. And I want to figure out what forces are acting on the box. And of course, it's near Earth, so it's got a weight force. And weight forces always point straight down towards Earth. It's a little bit messy there. Maybe I should draw it on the board so it's a little bit bigger. I'm not sure if it's clear enough that everybody can see it from home. Let's draw the free body diagram nice and big. So I've got the cartoon, kind of looks like this. Here's my 8 kilogram box. This is 25 degrees. And I've taken my axes like this. Now I'm going to redraw that in a free body diagram because I don't have any forces in there yet. And in my free body diagram, I tend to, you don't have to, some people don't do this, but since my box is kind of at an angle, I still draw it at an angle. Gravity always pulls straight down towards the center of Earth. Even when something's on a plane, it's still pulling in that direction. The plane is exerting a different force. But so the length of this vector that I'm drawing right here is going to be 8 times 9.8 in SI units. It's an 8 kilogram box. So that's mg I'm putting next to it. Just labeling the length of that vector. And let's see, we're going to introduce a new force now called the normal force, which means that if there were no other forces, this thing would just be in free fall, it would be going down, it wouldn't stay on the plane at all. The plane is keeping it from moving through this direction. It can't go down through there. It's got to stay on the plane. Now, when the plane is frictionless, what that means is the plane cannot exert any force on the box along the direction of the plane. You know, you can imagine if the plane were exerting a force, maybe I'll write this, F from plane. If it were like that, that force would serve to slow it down as it was going down. That's what friction does, right? Well, that's exactly how we're going to implement a friction force. So the statement that there's no friction, that this is a frictionless plane, means whatever force the plane is exerting on this box cannot have any x component, because that would slow it down, or even weirder, it might speed it up, but there's no reason to imagine the plane is actually like giving it some extra energy or acting like a motor. So when it's a frictionless thing, the plane only exerts a force on that box in the direction perpendicular to the plane when it's frictionless. Any component parallel would act kind of like friction. And perpendicular, normal is another word that means the same thing as perpendicular. So that's why we call this the normal force that you read about in the book. And a lot of times, I sometimes will label it as just N. That looks like newtons. I noticed, I think Giancoli labels it as Fn, the normal force. That way you won't get confused with the newtons thing. Okay, so, and that force is going to keep it from going through the plane, right? It's not going to crash through the plane. The plane, it keeps adjusting it bigger and bigger until it keeps it from going through. Any other forces acting on it besides gravity and the one force that the plane is exerting on it, which we're calling a normal force here because it's frictionless? I don't think so. We're going to ignore air resistance. At least that was what was implied by this, even though I should have probably said it explicitly. No friction. So those are the only forces. And I said, let's be fearless. I'm going to take one plus x direction down the plane plus y perpendicular to the plane along the direction of the normal force. And then I want to do the sum of the force. You know, I know I want ax. That's the answer to the problem I'm after. So I'm just going to go for it and write down Newton's law x components, because that's the thing I want, right? It's always good to write down an equation you want. I may find that I have to use another equation sometimes to substitute in something, but I really like to go for it and just have the thing I'm going to solve for there. I've got to get the x components of these forces. So let's start adding in the ingredients of the left-hand side. What's the x component of the normal force? Zero, because in going from the tail to the tip, I don't have to move along x at all. I'm only moving along y. So if you ever forget what components mean, just go back to that simple definition. Going from the tail to the tip, go along x and then go along y. I don't have to go along x at all. It's all along y there. So I'll put in a 0 placeholder. Of course, you don't have to put a 0 in there. What about the x component of this force that's going straight down? Now, this is what x means. Positive, negative, or 0? Let's just figure out the sign first. It's negative, right? Because I wanted to agree with you. It looks like it's positive to me. In going from tail to tip, I was about to agree with you till I looked at the diagram. In going from tail to tip, right? What I've got to do is first move along x and then move along y. Moving along x, am I moving in the negative x direction now? Oh, positive x direction, right? And then just along y to bring me straight to the tip. So this is what we're finding out is there's a positive x component to this weight force, and there's a negative y component because we're moving along the negative y component there. All right, so that positive x, we're concerned with x components here, so I'm going to put in a plus sign. And the magnitude of this, maybe I wrote this in not such a good place. The hypotenuse over here is 8 times 9.8. My goal is I've drawn a little right triangle, even without thinking about it. And the x component magnitude is how long this side of the right triangle is. And I know the hypotenuse, right? We know the length of the force vector, but we want to find that projection along the x direction, which is this side here. If I only knew an angle in there, I could use my trig knowledge, SOHCAHTOA, or the way I do it. But do I know any angles in there? And the answer is kind of yes. We haven't used that 25 degrees. Let me just try to draw the relevant things over here. I didn't do the best job of drawing something horizontal there, but here's my force vector going down. Can anybody, for example, tell me what this angle is up here if this one's 25 degrees? $65, right? They've got to add to 90 because the three have to add to 180, and this is definitely a 90-degree angle down there. So these two have to add to 90. 65 plus 25 is 90. So this is 65. That's good. We've drawn a, let's see, I guess if I look at my triangle over there, I drew something that looks like this. So I do know now an angle in here. This angle is 65 degrees. If you like, I could have also, if I drew a line going straight down like that, this angle would also be 25 degrees. So if you want to directly put one over, you might remember that that angle belongs over there. It kind of looks like this is the small angle, 25 degrees there. And this one would be the complement of it, but no, the one that has to add up to 90 degrees. But in any case, that's 65. So how do I calculate this side length of the right triangle? Hypotenuse length, 8 times 9.8. Do I multiply by the cosine or the sine? Ooh, we've got some disagreement here, cosine or sine. Well, you know what? For me to get over there, I think of it this way. I pivot through the angle I know, and I really like that. It's satisfying to pivot on that little hinge that I've drawn in there, right? When I pivot, when I'm satisfied like that, do I choose the cosine or the sine? The cosine. You just got to remember that. But for some reason, I think of the cosine comes first because it went with x in the way my teacher taught it back in high school. So this is 8 times 9.8 times the cosine of 65. I couldn't put it right there. There just wasn't enough room. And therefore, I've already decided that comes in with a plus sign because it's a positive component, right? So 8 times 9.8 times the cosine of 65 degrees gives me the x component. Okay, so there's a component of the normal force. There's the x component of the weight force. Seems like that's it. The mass is 8 kilograms. And well, I'm after ax, and that's the only variable left in there. So I can just solve for ax, right? That looks good. I think what I'm going to do is let you finish the rest of this problem. So spend a couple of minutes. There's not too much to do here. I'm going to go back to the PowerPoint slides just because it's on there in case anybody doesn't have it in front of them. So we're kind of at this stage right there. Find the magnitude of the acceleration down the plane and then how far it moves in the next 2 seconds following being released from rest. Okay, the AX is an easy one-step kind of thing here. Once I get rid of the 0 there, I can cancel out the 8 on both sides, divide both sides by 8, and I just have to calculate 9.8 cosine 65. That's going to make it a little bit less than 9.8, so 4.14 is what I get after finding AX. And then what if I wanted to calculate how far it's moved? Let's suppose I release it from rest here. 2 seconds later, it's down there. How far has the front of the box moved down the plane? What kinematics equation can I apply to get directly to that answer? The second one, and Is that the one with the t squared, the t, or the v squared? The t squared. Okay, I like that too. X is equal to x0 plus vx0 times t plus 1/2 ax t squared. Okay, I could just subtract off x0 onto this side and write it that way. This is how far it went since t equals 0. That's what we want to find, x minus x0. It's displacement since time 0. What's vx0? 0, it's released from rest. What's ax? 4.14. Yeah, the sucker answer might be 0 because you're used to thinking of things in free fall and x is horizontal, but we're not even close to that. We just found ax is 4.14. So this is 1/2 4.14, and it was 2 seconds. So we got to square that. That is 8.28 meters. Good. All right, so we figured out about weights, normal forces. We got about 7 minutes left, so let's introduce another thing. Okay, we did that. Here is a more complicated situation. It's more complicated because it involves 2 boxes and they're being pulled along a floor. Now in this case, we're told the surface is frictionless if you read that last sentence. So once again, the friction's not pulling it back. There's no grinding against the surface. It's like it's made of wet ice or something like that. So someone's applying a 5 Newton force to the end of the string over here, right? These things are just sitting on a frictionless plane. You have the intuition that it's going to start accelerating in that direction. And our first goal is, well, I guess the first thing we want to answer is which block has the larger acceleration when they start moving? Before I answer that, the other complication here is that there's strings, and we need to know a little bit about how to think about strings. And so let's talk about the general properties of strings that we're always going to count on in physics 110. They may not hold true in more complicated situations. So we're going to always count on these things that can simplify your life a lot in physics 110. But they could be called into question in more complicated contexts. So here's a different problem. I've got the ceiling here, and I've attached mass m1 via a string to the ceiling, and then hanging from the bottom of m1 is another string attached to m2. That's sort of a complicated thing. We're going to assume that when you see something called a string or a cable or a cord, even though cables sound really hefty, we're going to assume that they all have a negligible mass compared to the things that they're attached to. So, we'll usually refer to this as a light string, but, even if you see a cable or a cord or a wire or anything like that, we're going to assume they're massless, always in physics 110. So regardless of how a homework problem is phrased, we just don't have the tools to take into account ones where the mass is non-negligible. Okay? So look at the objects it's connected to, and it should be massless compared to them, essentially. When we talk about strings, we often use the word tension. Okay, and the tension means how taut the string is. So we're first of all going to assume that the tension doesn't change as you move along a continuous piece of string, right? The tension down here might be different than the tension in this string. It probably is. But as I move through a continuous piece of string, the tension doesn't change. That wouldn't be true if I have a really massive piece of string, right? Because there's more weight hanging below the top than there is below a point at the bottom, right? So the tension wouldn't be as much as the bottom, and it would be bigger at the top. But our string is massless. So we're going to assume the tension is the same all the way through a contiguous piece of string. But different string parts can, there could be a different tension, T1 and T2 in those parts because they're not one unbroken piece of string. What does the tension mean? If I know the tension, so the tension is a force. It has units of newtons in SI units. And if the tension is 5 newtons in this string, what that means is it applies a 5 Newton force to each of the things that it's attached to at the two ends, and always in the direction toward the inside of the string. So whatever the tension is in this top string, it's applying that tension force upward on this mass here. It's also applying an equal force downward on the ceiling up there, because the tension is the same all the way through. So that's how you use the tension. It allows you to know what force is being applied to the various objects that it's attached to. So we'll call that a light string. Okay, we won't have a chance to get through all this problem, but let me just talk through the first few points and ask you guys about it. Which block? So we're going to start pulling this. Of course, they're going to accelerate, but which one's going to have the bigger acceleration as I pull it faster and faster in that direction with my 5 Newton force I'm applying with my fingers? Block A. What's the evidence for that? Okay, certainly true. Although the gravitational force is in the perpendicular direction to the direction I'm trying to accelerate it. Yeah. B will have, okay, so the opposite. Yeah. B will have a larger acceleration. Why? Well, you maybe have solved part of this problem that everybody else hasn't, but I'm going to say neither of those are correct. Actually, both of them have the same acceleration, and at least one person is nodding their head. Anybody want to say why it makes sense to say they both have the same acceleration? Yeah. Yeah, they're kind of, for all practical purposes, they're moving as a unit, right? The middle string stays taut the whole time. And as they move, at every moment in time, they have the same velocity, right? Acceleration is just the rate of change of velocity. And if they both have the same velocity at every single time, they may as well be glued together by a rod and just be one continuous unit, right? It's not like the left-hand side of a box has a different acceleration than the right-hand side of the box when it's sliding along. So it is here. These things move as if they're a unit. At every moment, they have the same velocity, and therefore the rate of change of their velocity, which is the acceleration, is the same for both of them. Okay, so the answer for A is both are the same. Most people don't have that intuition, in my experience, whenever I ask that. But it's an important point. We're going to use it as we go on. Maybe I think we better stop here. It's 4 p.m. And we'll continue with this on Friday. Then we'll talk about pulleys, then we'll talk about friction, and then we'll be done with chapter 4. We'll see if we can do that on Friday. Okay, so it's a good time to get into that chapter 4 homework now that you've got chapter 3 finished. Our exam is on Wednesday. I have it nominally due Monday night. And that's to force you to do it early enough and complete it so that you have a chance to review, do your final review. You don't want to be doing the homework the night before the exam, I hope. See, if you have lab tomorrow, have fun. You'll be doing some kinematics practice in there, and I will see you on Friday.
Hey, Dr. Kelly.
Yes.